Let's go ahead and talk about capacitors. Now, the capacitor we have talked about so far is called a parallel plate capacitor. Specifically meaning too large for their size or for how far apart they are, plates that are parallel to each other. One of the plates ends up, once it has been charged, one of the plates has a positive surface charge density. The negative plate has the same magnitude of charge density, but of course it's negatively charged. Eta, this charge density, is the same magnitude for both plates when they're charged. With the way I've drawn my picture, the electric field between the plates will point left to right, because we already know electric field lines point away from positive charges and towards negative charges. We also already talked about the magnitude of the electric field being the surface charge density divided by epsilon naught. Okay, that is specific to a parallel plate capacitor. When we talk about potential difference, and starting with the fundamental equation for potential difference, since the electric field is uniform, I can bring that out of the integral. Integral of ds is delta s. The dot product, of course, means that we only care about the direction delta s that is parallel to the electric field. So for our capacitor, if we want to talk about a potential difference across the plates of the capacitor, then we have two choices. We can either say our initial position is the left plate. The final position would be the right plate. We could also make the initial position the right plate and the final one the left plate. That's our two choices. The dot product means we only care about these components that are parallel. Let's go ahead and keep what I've already drawn. So our initial position as far as delta S is going to be the left plate. The final position will be the right plate. So if I wanted to write delta S as a vector, I would write it as whatever distance ended up being between the two plates. The direction of delta S in this specific picture would be I hat. It's to the right, so in the x direction. So coming down, I'm going to put in E. The magnitude is eta over epsilon naught. The direction in my picture, this specific example, is in the x direction. We're dotting this with that distance d, the distance between the plates, which is also in the x direction, according to how I chose initial and final. So delta V ends up being negative eta over epsilon naught times d. And as a reminder, I dotted with I is simply the number 1, which I'm not going to write the number 1. We could if you want, but there's no direction on our answer. So the delta V for specifically this parallel plate capacitor is equal to negative eta over epsilon naught times d. As we talk about capacitors, we are typically going to go ahead and look at just the magnitude, Because we already know that electric field lines point from high potential to low. Getting this negative sign in our equation means we ended up at a lower potential. The final voltage is smaller than the initial voltage. That's its meaning. We already know this. This is always going to be true. The delta V, if we go from the positive plate to the negative plate, is always going to be negative. So typically, when we talk about delta V for a capacitor, we talk about absolute value. And we do so without writing the absolute value signs. This equation is specific for a parallel plate capacitor. Now, capacitors don't technically have to be parallel plate capacitors. They could be like two little spheres where they end up with the same charge but opposite charge, so two charged spheres that end up with an electric field between them. A capacitor is essentially something that gives us this nice electric field, which in turn ends up allowing the capacitor to store energy. A generic term for plates or little spheres are electrodes. So we would have a positive electrode and a negative electrode. You're going to see that terminology once in a while throughout the book as well as throughout our homework. So just be familiar with that. The electrodes themselves, the electric field between them would be different, but we would still end up with some sort of potential difference between these electrodes. And since we're saying these electrodes make up our capacitor, we call this the delta V for our capacitor. So delta V sub C specifically means the potential difference across a capacitor. It does not mean the potential at a specific point, but that's okay. We don't end up needing to know that. This potential difference is what is important to us. Now, capacitors themselves have a value that we call capacitance. We can think of capacitance as something along the lines of the ability to store charge and in turn store energy. Capacitance is defined as essentially the charge that accumulates on either electrode, both electrodes, whether we're talking something like the two small spheres or even the parallel plate. Each plate would be considered an electrode. Both plates will have the equal but opposite charge that accumulates on them. Okay? They also have the same charge density as well. But in our equation over here for capacitance, when we say Q, we mean the magnitude of the charge on either electrode. Regardless of what type of capacitor it is, parallel plate versus some other shape, either way we mean the charge magnitude on either electrode. Or if we're talking specifically parallel plate, the electrode is a plate. We also find, as far as definition of capacitance and its ability to store charge, we find that this capacitance is equal to the charge over this potential difference, delta V, that we've already been talking about. This equation is a very fundamental basic equation for capacitors. But it is a tricky equation in that Q and delta V do not determine C, the capacitance. Okay. That means if I change Q on a capacitor, that does not change C. If I change Q, it changes delta V. This is similar to waves when we talked about waves. And I said that the speed of the wave is wavelength times frequency, and told you this is one of the hardest equations, which sounds very silly, but it was hard conceptually in that the speed of the wave was only determined by the medium. So we have a situation here where the capacitance is not related to charge, it's not determined by, I should say, by charge or delta V. It is true that if I know Q and delta V for a particular capacitor, then I can certainly use the values to calculate C that way. But I cannot change Q or delta V and expect C to change, the capacitance. Okay, so a couple words of warning here. This C is a variable, meaning it represents a specific characteristic of our capacitor. It specifically represents capacitance. Charge has units of coulombs, which we use capital C for as well. So just be careful in terms of making sure you understand whether we're representing capacitance. That will always be as C equals some number, or charge is some number of coulombs, or microcoulombs, or nanocoulombs. So just pay attention, make sure you are paying attention to capacitor versus charge, that sort of thing. Units of capacitance. Well, charge is in coulombs. Delta V is in volts. So units of coulombs per volt is what capacitance is measured in. We call this a farad, as in Michael Faraday, and we use a capital F to represent that. So a capacitor could be like 10 microfarads. So C equals this. C equals 50 microfarads. There's multiple set values of capacitors that we can purchase if we wanted to. There's not an unlimited number, but there are many values that we can purchase. But again, the C would represent that it's the capacitance, the micro F would be the microfarads. So units of capacitance. All right, so in terms of affecting or determining capacitance, let's go back to our parallel plate capacitor over here on the right. Now that we have stated that capacitance for any capacitor at all is equal to the charge that accumulates on either electrode over delta V, let's manipulate our delta V equation specifically for the parallel plate capacitor to see how we can get to capacitance. Eta, if you remember, is charge per area. So this same equation right here turns into Q times D divided by that surface area times epsilon naught. What I want to do is write this as Q over delta V because we've already defined capacitance as charge per voltage. If I rearrange this voltage equation for Q over V, I get epsilon naught times A over D. This is equal to the capacitance specifically for a parallel plate capacitor, and it assumes a vacuum between the plates and essentially air. In our current test notes, when you look at the test notes, you'll find that equations for capacitance are spread between two pages, the bottom of page 9 and the top of page 10 in our current test notes. At the top of page 10, they call this a C naught. So C naught meaning the capacitance if there was nothing between the plates of the capacitor. The capacitance is determined by physically how the capacitor is constructed. Here it depends upon the cross-sectional area of these plates that face each other, that are parallel to each other, and it depends on the distance between those plates. Okay, it is common to have a material between the plates. I've grabbed a picture from our book, the Randall Knight book. The material that we would potentially put between the plates is called a dielectric material. A dielectric material is one in which the atoms are polarized or easily become polarized as electric dipoles. Pole. And when we have our capacitor that is charged, that has an electric field, these electric dipoles, those dipole moments, if you remember, P, line up with the electric field of the capacitor itself. But what that does, the dipole moment, if you remember, points negative to positive. It's the lighter arrow in the picture. It's in the same direction as the original electric field. But what happens is that we now have an induced electric field. That's what they're labeling here. So these arrows are representing the actual electric field now that's been created because this dielectric material is polarized. And that E induced is what we're calling that. Those dipole moments line up with the electric field of just the plates. When they do that, it actually decreases the strength of the overall electric field between the plates now. If you compare the length of these electric field arrows on the left, where we had nothing between the plates, to the length of the arrows in this right-hand picture, they're representing the addition of the original electric field plus these new little electric fields because of the induced dipoles that gives us an overall electric field between the plates that is a bit weaker. Ultimately, having a dielectric material between the plates increases capacitance. You'll see an equation that looks something like this. This K-ish looking value is called a kappa. It's a Greek letter that I don't write super well. It represents what's called the dielectric constant. This is something specific to the material. A dielectric material is not just one specific material. It is a category similar to how we use the term conductor to mean materials that easily share their valence electrons. It doesn't mean just copper or just aluminum. It means this whole category of materials that behave in a similar way. Similarly, the term dielectrics represents materials that behave in this way where dipole moments are created when they're in the electric field, and those dipole moments line up with that field. Our book has some examples of dielectric constants. For example, Teflon. I'm just grabbing some materials that I'm seeing. 2.1 is the dielectric constant of Teflon. It does not have units, it's just a number. But this number is bigger than 1, and that means whatever capacitor we had, or capacitance, I should say, we had without Teflon in it, as soon as we slide Teflon into that full area between the plates, the capacitance will be 2.1 times bigger than it was before. Pyrex glass. The dielectric constant is 4.7. So putting Pyrex in would result in an even larger capacitance, 4.7 times bigger than what it was without anything between the plates. All right, so these dielectric materials increase capacitance, which means, as I slide down here, if they increase capacitance, that means that capacitor can now store more charge. Because if I increase the left side, something has to change on the right side. We can think of that as increasing the charge that can be stored on the plates, which, if we think about the parallel plate capacitor, if I have more charge, then the electric field between the plates would get stronger than it was before. Okay. Well, that's counterintuitive to the picture we just looked at, though. Ultimately, that ratio of charge per potential difference gets bigger, which results in more energy stored with a bigger capacitor. So by putting a dielectric constant into a capacitor that previously did not have one, increases the capacitance, and in turn, an increased capacitance will store more energy. Capacitors store energy. We're going to use a capital U because that is the symbol we've been using to represent stored energy. In the test notes, we have U sub cap, C-A-P. I tend to just use U sub C meaning the energy stored in a capacitor specifically. One way we can write this is 1/2 C, meaning capacitance, times delta V squared. So the energy depends on both capacitance and potential difference across the plates. But using this equation right above it, here, for example, in place of C, I could put Q over delta V. When I do that, one of the delta V's will cancel, so the energy could also be written as the charge times the potential difference. But I could also substitute in place of delta V. If I manipulate that top equation up here, delta V would be Q over C. So if I put that in for delta V and square it, one of the C's will cancel in the denominator, and we can write the energy stored by a capacitor in terms of the charge on the plates and the capacitance. So we can write the energy in terms of any two of the three variables because they're related. The test notes has this one, the 1/2 C delta V squared, but you can easily come up with any of them because we have this relationship as well. So this represents the energy stored by a capacitor or in a charged capacitor. It's energy stored though, and that energy in turn can be used to do work, to cause charges to move quickly through a circuit. A common example would be the flash on a camera, particularly the older cameras. I don't know how these beautiful cell phone things work at this point. But ultimately, a regular camera, the battery would not be sufficient to cause a flash. And so a capacitor would be in the camera itself. And when you press the button to take the picture and also cause the flash to light up, the bulb to light up as the flash, it was actually the capacitor discharging, meaning the capacitor, these plates of some sort, had been charged. And discharging means we provide a path through the little flash to the capacitor. We've disconnected the battery. When we do that, the charges will not remain separated. They will move to get back to an equilibrium. And so we end up with a current flow that does not last for very long, but it's a relatively large value in a very short time frame. We'll be talking current more in the next couple of chapters. We do use the definition that Benjamin Franklin came up with, in that positive charges move, which of course now we know is incorrect, but we still use that definition just because it's still valid, essentially. We know technically it's the electrons that can move from atom to atom in a conductor, but current we define as positive charges. Even though they're not technically moving, mathematically positive charges moving counterclockwise in my picture are mathematically equivalent to negative charges moving in the opposite direction. That is a story for our next couple of chapters, though. Okay, one last equation we're going to see that is energy. It's called energy density. Oops. They write this as a lowercase u sub e. This is our little epsilon naught constant we've been using. And then capital E is the electric field. The energy that is stored because of that electric field that exists between the plates. It's all about having an electric field between the plates. What this energy density represents is the stored energy of our capacitor divided by the volume. So coming back to my little picture up here, there's a certain volumetric region between the plates where the electric field exists. That's what we mean by volume when we say energy per volume. And this is to allow us to see that the energy boils down to the fact that we have an electric field. In the next video, we're going to talk about having a capacitor connected to a battery, as well as having more than one capacitor connected to a battery as well. And then we will do some examples to finish off this chapter.